To start talking about polynomial division with remainders, we're first going to look back at an example that does not have a remainder. So this was the example that we covered today in the warm-up. And as you may notice, and as we've talked about, when you use this area model, the diagonals match what is written on the outside. So x squared is equal to x squared. Negative 7x plus 2x is equal to negative 5x. And negative 14 is equal to negative 14. What I want us to focus on is the fact that we had that part where it says negative 14, and that matches the negative 14 on the outside. So what that indicates to us is this is a perfect area model, that when I multiply this factor times this factor, I get exactly x squared minus 5x minus 14, because that's what's on the inside of this box. Now, what would happen though if that wasn't true? What if this wasn't negative 14 and it wasn't the same? Then we wouldn't have the exact correct area. So let's look here. I'm going to do a really similar example here. I'm going to do it using both methods. I'm going to start with the area model, but then I'll get to long division. I'm going to change this problem slightly. Instead of minus 14 at the end, I'm making it minus 16, and we're going to see how that affects the results. So I'm going to set up my area model. The difference in degree is 1, so within my box I'm going to draw one vertical line, and I have 2 rows for the x plus 2. And then I have x squared minus 5x minus 16. And then I'm going to work through this. First thing we always do is we bring the x squared, or whatever term is right here, you bring it into the first box. And then once you've done that, what you follow is a pattern from then on. You factor, you multiply, you subtract. You factor, you multiply, you subtract. So first I factor. I find if I need x and something else to multiply to x squared, I'm going to have x times x. I'm then going to multiply x times 2, because those meet. The vertical and the horizontal meet in this box right here, so I multiply those to get 2x. And then what I'm going to do is I subtract. So I'm going to take negative 5x minus 2x, gives me negative 7x, and I'm done my first cycle. I factored, I multiplied, I subtracted. Now I'm going back to factoring. So if x is one of my factors, my other factor is going to be negative 7, because negative 7 times x is negative 7. And then I will multiply negative 7 times 2, because this is the box where they meet. Now what you'll notice is the same exact thing has occurred inside the box, even though I changed the constant there. But if you look here, negative 16 and negative 14 are not equal to each other. If that's the case, what that indicates is we have a remainder. So when you divide this polynomial and it comes out to x minus 7, that is not a perfect division. We're not completely done. There is some amount that is unaccounted for. So what we do is we continue this pattern. So we factored, we multiplied, we subtracted, we factored, we multiplied. I'm going to subtract again, as if there was something else in this row. I need to figure out what combines with negative 16 to add, or sorry, what combines with negative 14 to actually give us this total of negative 16. So I will do that just like if I was subtracting in any other row. I take this outside number, negative 16 minus negative 14. And I'll rewrite it like this. And since minus and negative is the same as addition, it becomes negative 16 plus 14, and I find that my remainder is negative 2. That's all fine and dandy, that my remainder is negative 2. How do I write that in terms of my solution? Because my solution is going to be a polynomial, right? I'm looking here. I thought my solution was going to be x minus 7. How do I include my remainder in that answer? You're not just going to write that it's a remainder of negative 2. You're actually going to put that back in the format of the polynomial. So if you recall back to when we divided 2 into 51 and, this all happened, we had a remainder of 1 at the bottom. And I said, because that 1 was unaccounted for in 51 divided by 2, essentially what came out of the long division was the answer for 50 divided by 2, but there was still 1 left. So when you divided 50 divided by 2, and you got 25, there's still 1 left. So you still have 1 out of this 50 left. So if you take away the 50, there's a half. So basically, it was our remainder of 1 divided by the original divisor of 2. We're going to do the same thing with polynomials, as we will take our remainder of -2. But we are going to divide it by our original divisor of x plus 2. And then once we do that, we just sort of write that at the end of our answer, and we're adding it on. And my solution to this division becomes x minus 7 plus -2 over x plus 2. And now I'm going to show us that with long division. So one, this will show you a different method of dividing, but I also think it will help solidify how you work with remainders. So I'm going to set up this long division. We have x plus 2 on the outside of the symbol. Ooh, that's a bad 2. And then we have x squared minus 5x minus 16. X goes into x squared x times. That leaves me with x squared plus 2x. I subtract that. I'm left with 0 minus 7x. How many times does x go into -7x? -7 times. You'll recognize these numbers from the area model because, again, it's the same math being done in both models. It's just a different way of organizing it. -7 times x. Oh, I forgot to drag this down. -7 times x is -7x. -7 times 2 is -14. And then when we subtract here, we see that we naturally come to this place where I have that -16 minus -14, which occurred in the last problem as well, and gives me -2. And at this point, my remainder is -2. And the reason I know that I'm at the point with my remainder is because, again, there's nothing left here to drag down. I'm out of stuff to drag down. So my remainder is -2, which basically means that, if I had had x squared minus 5x minus 14 here, like I did originally, then my answer would have been x plus 7. But I don't have minus 14, I have minus 16, which is like an addition of -2, right? So that's how much remainder I have, is -2. And so what I'm going to do is, if I still had that -2 left in the numerator, I represent that here over the original divisor of x plus 2. And again, just like in the last problem, my answer turns to x minus 7 plus -2 over x plus 2. In summary, everything else is the same. The actual division is the same, but when you get to the end of the problem, you'll find a remainder. What you do is you take that remainder and you just add it to the end of your problem, but you have to divide it by the original divisor, or in other words, the original denominator. And then it'll give you your answer.